Welcome to 34th lecture in the course of Industrial Engineering and Operations Research. We are discussing linear programming problems, how to solve linear programming problems. So, one method was told graphical method, but which can be used only for two variable problems. If there are only two design or decision variables, then you can use that method. Then there was a simplex method. Now, in the simplex method, we discuss some problems, but we will discuss other problems also, and sometimes what happens that it becomes very difficult to choose a basic feasible solution, because in simplex method we have to obtain initial basic feasible solution. So, sometimes suppose this is your feasible zone. Okay, so as I told that solution lies in the corners. So, you have to start from one corner, maybe suppose 0 0, and then you move to another corner, then you move to another corner, like that you have to do that. So, at least one starting solution should be there. If your constraints are of less than type, that suppose x plus 5y is smaller than 10, then you can put a slack variable and you can make x plus 5y plus s is equal to 10, and in the beginning you can take s is equal to 10 itself. So, starting solution is obtained like that. Okay. But however, in other cases you may have some difficulty. Say for example, you have been given a problem, minimize z is equal to 4x1 plus x2 subject to 3x1 plus x2 is equal to 3. Now, this is equality constraint. I will not add any slack and surplus variable here. Then you have 4x1 plus 3x2 greater or equal to 6, and x1 plus 2x2 is smaller or equal to 4, x1 x2 greater than 0. So, here this constraint I can easily convert to this one. Say I can say x1 plus 2x2, and maybe I can say that this is say s1 is equal to 4. Okay. If I put x1 is equal to 0, x2 is equal to 0, I get s1 is equal to 4. But here I have to put some, in fact I have to put some surplus variable here. I have to say that 4x1 plus 3x2 minus maybe s2 is equal to 6. So, if I put x1 x2 is equal to 0, then my s2 will become minus 6, which is infeasible. And similarly, if I put x1 x2 0 here, to 0 is equal to 3, this is also not satisfied. I do not know what to do about that equality constraint also. So, the problem comes when you have got equality constraint and when you have got greater than or equal to sign. Then what to do that? In that type of situation, there is a difficulty. Okay. So, till now, because in last class we solved the problem in which all the constraints were of this type, okay, less than or equal to. So, we had starting basic table very nicely, because all the slack variables were treated as a basic variable. But here what to do that? So, there are two methods to tackle this type of problem. One is called big M method, other is called two phase method of simplex. So, first let me explain big M method. So, what we do that we produce, whenever we do not get a slack variable, then we put two artificial slack variables R1 and R2, means not 2 means as many as this one. In this two were not having any slack variable. So, we put there and consider a very big number m. So, we make, suppose this is a minimization problem. So, minimize z is equal to 4x1 plus x2, we want to do that only, but we have done plus mr1 plus mr2. That means m is a very big number, it may be 10 to the power 6 also, but usually if you take sometimes even 100 or 150 also, that is also enough, but it should be somewhat bigger. Okay. So, mr1 plus mr2. So, when you will minimize that thing, then tendency will be to get the values of R1 and R2 0 because they have been added artificially, they should come 0. So therefore we are minimizing, but we are trying associating coefficient m with artificial variables, and those coefficients are high number. So subject to now, so what we are doing, 3x1 plus x2 is equal to 3 was there. So we added plus R1 equal to 3. So this is artificial variable we added. Next was 4x1 plus 3x2 minus x3 greater or equal to 6. You see it is 4x1 plus 3x2 was greater than 6. So surplus variable will be added, that may be 4x1 plus 3x2 minus x3. But on top of that we added a slack variable plus R2 is equal to 6, and the third one is that x1 plus 2x2 plus x4 is equal to 4. It is a natural slack variable that also has come here. Now condition is that x1, x2, x3, x4 and even artificial variables should be greater or equal to 0. As m is very large, solution of it is likely to make R1 and R2 equal to 0. That is the thing. So let us make that now. Now we have got 3 slack variables, and for 3 equations we need only 3 basic variables. So let us make that table. So starting table is that basic z r1 r2 x4, and we write z row x1 x2 x3 r1 r2 x4 and solution. So x1 coefficient is 4, so minus 4 minus 1 0. This coefficient was minus m1, this is minus m, coefficient was m, so therefore other side it will go, it will become minus, and this is 0 0. R1 row means first row, that here coefficient of x is 3. So 3 1 0 1 0 0 3, in this coefficient of R1 is 1. Then R2 row means the row in which R2 is there, that 4 3 minus 1 0 and coefficient is 1 0 6. Then x4 slack variable 1 2 0 0 1 4. You see the coefficient of x4 here in the column is 1. Now this table has been made, but this table is not consistent, because what it is saying that R1 is equal to 3, R2 is equal to 6, but in the objective function R1 and R2 is there. So basically z should be 9m, because 3 plus 6. So what we have to do, that make the table consistent by multiplying second and third rows by m and adding in z row. So what you do, that you multiply m by R1 by m and R2 also by m and add in this table. So if you do that, so 3 plus 4 7, so 7m minus 4 plus 7m, 3 plus 1 4, so minus 1 plus 4m minus m only, this is 0, this is, if you add that m minus m plus m 0, this is 0, and solution is 9m. So this table is consistent, it is doing everything right. Now we have to decide that which can be the entering variable and which can be the leaving variable. So we observe here that entering variable should be most positive, because it is a minimization problem. In minimization problem it should be most positive. So therefore what happens, that this is x1 and this is r1. Okay, so this will go like that. So now x1 becomes entering. Why it is entering? Because it is most positive. 7m is much bigger than 4m. So this is this one. So it becomes a pivot column, and therefore it's you divide solution column entries by coefficients of this pivot column. So you have to say, you can put a ratio table here. You can say 3 by 3 is equal to 1, and then 6 by 4 is equal to 1.5. Then you can say 4 by 1 is equal to 4. So among them the minimum ratio is 1. So therefore R1 becomes the leaving variable. So I have marked it R1 as a leaving variable, it will go and the other thing will come. So therefore next table will get modified. We have put x1 here, but then x1 coefficient was 3. So this becomes the pivot row and pivot column, pivot element was 3. So divide everything by 3. So this is 1, 1 by 3, 0, 1 by 3, 0, 0, 1. So we have normalized everything. 3 by 3 is equal to 1. And then what do we do that? After that, above that, by row operation, you make all the entries in x1 column 0. So in the x1's coefficient was minus 4 plus 7m. So therefore you multiply whole thing by minus 4 plus 7m and subtract in that. So if you do that, this becomes 0, but if you do that, this will come 1 plus 5m by 3 by by multiplying 1 by 4 minus 4 plus 7m, and then you have to subtract that. Then you will see that it will come, yeah, you multiply that here in 1 by 3, that much quantity, and then you add, it will come 1 plus 5m by 3. Similarly, this will be minus m, this will be like this will be 0, this is 0, this is 4 plus 2m. And same thing you do in the other one. R2's coefficient was basically, what was the coefficient of R2? R2's coefficient was this one, 4. So what you have to do, that you multiply whole thing by 4 and subtract it here. So 4 minus 4, 0, and here you have to say 4 by 3, and 4 by 3 will be subtracted in 3. So 3 minus 4 by 3 is 5 by 3, like that. So it is 2. Similarly, you do for third row also. Here also you make the coefficient 0, and this becomes 5 by 3, this becomes 0, minus 1 by 3, 0, 1, 3. So like that it has come. Now at this stage you can check also little bit, okay. X1 is equal to basically now coming 1, R2 is equal to 2, okay, solution, and x4 is equal to of course 0. And as you decided already, Z was basically objective coefficient was 4x1 plus x2, 4x1 plus x2, 4x1 plus x2 plus mr1 plus mr2. So R2 is not there in basic variable, so it is naturally 0, but mr1 means it will be 2m, and x1 is equal to 1, so 4 plus 2m. That is why the solution is coming 4 plus 2m. That means up to this more or less we have done, okay. And then let us go to the other one. Now you see the most positive coefficient here is what? 1 plus 5m by 3. Minus m is negative. 4 minus 7m by 3 is also negative, because m is a very big number. So therefore it is also negative. But 1 plus 5m by 3 is positive, so it becomes a pivot column. And now you divide that everything here, you find out ratio 1 by 1 by 3, okay, this is 1 by 3, so this becomes basically 3, and then 2 by 5 by 3, so this becomes what? 2 divided by 5 by 3, so 2 divided by 5 by 3, that means 2 multiplied by 3 by 5, so that means 6 by 5. And then similarly that here solution is 3, so 3 divided by 5 by 3, that means 2 multiplied by 3 multiplied by 3 by 5, so this becomes 9 by 5. So 9 by 5, 6 by 5, 3, among them 6 by 5 is the least, so therefore R2 becomes as the leading variable. So therefore in place of R2 now x2 will come, so x2 has come, this is x1, and now x2 is the pivot row. So therefore this is and x2's coefficient has to be 1, it was 5 by 3, that means divide everything by 5 by 3 or multiply everything by 3 by 5, then you get this 1 minus 3 by 5 minus 4 by 5, 3 by 5, 0, and this becomes 6 by 5, okay. Then x2 becomes the pivot column, so you multiply it by the appropriate things, so that above all the elements they become 0. So in the Z row, coefficient of x2 was what? 1 plus 5m by 3. So you have to multiply it by 1 plus 5m by 3 and subtract in the Z row, you will get this type of thing, and solution will come 18 by 5. Similarly, you have to do that in the for x1 row also and for x4 row also, and you get this type of thing. So at this stage you are getting what? You are getting x1 is equal to 3 by 5, x2 you are getting 6 by 5, x4 you are getting 1. this much you other things are 0, and your objective function was 4x1 plus x2, z was 4x1 plus x2 plus mr1 plus mr2. This was like this. So if we r1 r2 is not there in the basic solution, so therefore this is 0, but 4x1 plus x2, so 4 times x1 means 3 by 5 plus 6 by 5, so this is 18 by 5. So solution has come 18 by 5. Now is it everything optimized? No, not yet, because there is one column which is in the z row. We can see that x3's coefficient is still positive, it is 1 by 5. 8 minus 5m by 5 is highly negative number because m is a big one. Another one is minus 1 minus 5m. So this is also very big number. So this is also not acceptable, and moreover we have eliminated them also. Only thing that x3 can now become as the entering variable. If x3 becomes the entering variable, if this becomes the row, then what happens that this is 1 by 5. So you just make this one leaving variable. So this is x1 coefficient is 1 by 5, solution is 3 by 5. If you divide 3 by 5 by 1, this becomes 3, and this becomes some negative quantity, negative. So we will not consider negative or infinity, and this is 1. So among them 1 is the lowest value, minimum ratio is 1. So x4 becomes the leaving variable. So remove x4 and bring x3 here. So we have brought x3 here, and this becomes the pivot row, and the coefficient is already 1. So we don't have to do anything, but we have to make all the entries above that 0, just like we do in Gauss elimination method. So multiply it by suitable values, like first I can multiply by 1 by 5 and subtract from the first row, I will get this one. So I will finally get this type of table, and seeing this, what we see that all the coefficients of this z are either 0 or they are having negative value, because 39 minus 25m, since 25m, m is a very big number, so that is why it is negative, r2 is minus m. So now the answer has come 17 by 5, 2 by 5, 9 by 5. So therefore solution is what? x1 is equal to 2 by 5, x2 is equal to 9 by 5, and x3 is equal to 1, and solution came as z is equal to 17 by 5. So this was a big M method. But let us do the same thing by two-phase method of simplex. So in the two-phase we solve that problem in two phases. In the first phase we don't minimize or maximize that original problem. Instead we just want to obtain a basic feasible solution. So we introduce the artificial variables as usual, as we have done same thing, 3x1 plus x2 r1 is equal to this one. But x1 plus x2, x2 plus x4 is equal to 4. But somehow we have to do something so that r1 and r2 become 0. So we say minimize r is equal to r1 plus r2, sum of r1 plus r2. So we solve this problem. We forget about the original problem. In this problem constraints are same, but the objective function has changed. It will be always minimization of r is equal to sum of the slack variables, okay, r1 plus r2. So we make that. Now the basic simplex table we will make as usual, the basic r, r1, r2, and we write x1, r's coefficient is 0, 0, minus 1, because coefficient of r1 is minus 1, this is minus 1, 0, 0, and this is r1 row as we have written earlier. M is not there, only thing that here 4, this is like that, x4 is equal to this thing. So we have done written in a very usual manner. So this is fine, that it is showing that r1 is equal to 3, that means artificial variable is 3, r2 is equal to 6, x4 is equal to 4. They are giving you very good starting basic feasible solution. However, that solution in the r row is 0, which is inconsistent, because r1 is clearly 3 and r2 is equal to 6, so it should have come 9. So what we have to do, that to make it consistent, just do row operation and add r1 and r2 to first row. So if you add r1 and r2 to first row, then what happens that you can do multiply it and you can do that. So, this will become consistent, that means this will become finally 9. Okay. And then and after that you do the simplex method as usual. I am giving you the final table. Finally, you will be getting like that, R will come 0, x1 will come 3 by 5, x2 will come 6 by 5, x4 will be coming 1. So, that means starting basic feasible solution is this: x1 is equal to 3 by 5, x2 is equal to 6 by 5, x4 is equal to 1. If your solution, final solution also contains R1 is equal to something and R2 is equal to something, any one of that, that means the solution is infeasible. But if it is a feasible one, then R1 and R2 will be 0. So, we got that thing and we can straightway use this table for next page. We can remove R1 and R2 from the picture. We can just scrap and we can write as usual. So, we make now we take the original objective. So, z is equal to minus 4 minus 1. So, we put minus 4 minus 1 and this is x3 is equal to 0, x4 is equal to 0 coefficient, solution is 0, and x1 I have written x1 row, x2 is equal to x2 row which we got, and x4 is equal to we got, but make it consistent. This table is inconsistent because x1 is equal to 3 by 5, x2 is equal to 6 by 5. So, it has to be made consistent with the objective thing. So, to make it consistent, multiply x1 by the coefficient of x1 in the objective function, that means multiply it by 4, and x2 where you multiply it by this one because objective function was, you have already seen that objective function was 4x1 plus x2. So, just you have to do, you multiply that thing by 1 and then you add that. So, it becomes 0 0. So, now you see this solution is already coming 18 by 5 and this is what this one. So, here we see that now only coefficient of x3 is positive. So, it is a minimization problem. So, this can be entering variable. Now, what about that by ratio? This is, you see that this becomes the pivot column. So, here it is 1 by 5. So, 3 by 5 divided by 1 by 5 is 3 and this is negative and this is 1. So, lowest is 1. So, x4 becomes the leading variable, and therefore, what happens that if it becomes the leading variable, then it becomes z is equal to 0 0. You have to do that operation, that instead of x4 I have written x3 and x3's coefficient is 1, and now by row operation I am making everything above 0. That means suitably multiply this coefficient by something and subtract in the above rows, so that corresponding coefficients become 0. So, you are getting solution as 17 by 5 and you got this one. So, you got solution x1 is equal to 2 by 5, x2 is equal to 9 by 5, x3 is equal to 1, and automatically you got solution is equal to 17 by 5. Otherwise, you can check also z is equal to 4x1 plus x2. So, 8 by 5 plus 9 by 5 is equal to 17 by 5. That means, we have not done any arithmetic mistake there. So, this is how that this method works. This is called two-phase method. So, which method should be used? M method is okay, simple, easy, but only thing, one difficulty is that sometimes you have to use say very big number and it may make some precision problem, some round up problem. Okay, sometimes if you take too small value of m, it may not be giving you proper answer. M has to be very big, and if you take very big number, then such type of difficulties may arise, because some coefficients are very small, some coefficients are big. So, round up difficulties may be there, but in two-phase method those type of problems are not there, but only thing you have to do problem in two phases. Okay. So, these are the pros and cons. Okay. Maybe for a small number of variables it is okay, any methods can be used, but if there is a very big problem, then you have to understand this point, that if you use that m method, you have to use proper value of m. Okay. And this may come by hit and trial also. Sometimes you may have to use some value of m and then increase or decrease the value and see that if there is any change in result. Okay. Because result change will not be theoretically, but it may come due to numerical difficulty. If you have one coefficient 1 lakh or 1 million and other coefficient is just 0.1, you can imagine what will happen in computations. Okay. Now, let us give some problem, that suppose another problem. Suppose we have to solve this problem using two phase and big M method, maximize z is equal to 15a plus 20b subject to a plus 2b is greater than 10, 2a minus 3b is smaller than 6, 2a plus b greater than 6. So, why this has to be used by either big M or simplex method? Because there is one, basically two greater than type of constraints. Okay. That is why it has to be used. Okay. So, if we do that by two phase simplex method, so minimize the artificial variable R1 plus R2, and first was that a plus 2b greater than 10. So, I put c as a surplus variable, I put a plus b minus c, and on top of that I do plus R1 also, which is a slack variable, but this will automatically will become 0 later on. So, is equal to 10. Another thing was 2a minus 3b smaller than 6. So, here is a real slack variable plus d is equal to 6. Third one was a 2a plus b greater than 6. Okay. So, here this is it is basically instead of 2a it is basically a. So, you know a plus b greater than 6. So, a plus b minus e plus R2 is equal to 6, and here a, b, c, d, e, R1 and R2 are greater or equal to 0. And we make the table minimize R is equal to R1 plus R2. So, R's coefficient is 0, 0, 0, everything 0, R1's coefficient is minus 1, R2's coefficient is minus 1, 0, and R1 row has been written like this. Okay, a plus b, d row has been written like this, R2 has been written last one, a plus b minus 1, 1 plus 1, and then c's coefficient is 0, d's coefficient is 0, e is minus 1, R1's coefficient is 0, R2 is there, R2's coefficient is 1, and this is equal to 6. Okay. So, we have done that type of thing. So, here, but this is not consistent because it is giving R1 is equal to 10 and R2 is equal to 16. So, in R row solution should be 16, R1 plus R2 is equal to 16, but it is not so. So, what you do, that R1 and R2 row is added in the R small r row. So, that means R1 plus R2, you do R1 plus R2, you get this one. Now, you see everything is this one consistent, this is 6. So, R1 plus R2 is equal to 16. So, this is consistent and you are getting that solution equal to this one and this is equal to this one. So, now it is consistent and you have to do what? Now, what you have to minimize, because you have to minimize small r. So, for minimization problem, you have to see the most positive coefficient. Most positive coefficient is of b. Okay. So, therefore, b may become pivot column. So, if you say that 10 by 2, that is 5, this is some negative thing, and this is 6 by 1, 6. So, it seems that R1 should be the leaving variable. Okay. So, R1 has left, in place of R1 b has come, and you have done the same way, that b's coefficient should be made 1. So, divide it by that coefficient, so that this coefficient becomes 1 and this one, and then you have to do some row operation, so that above and below everything becomes this one. Already there were 0 only, 0, 0. So, we do not have to change d and R2, but we have to multiply this by 3 and then subtract in the small r row, and we do that, then we are getting that r is equal to 1, b is equal to this thing, d is equal to this thing, and a is equal to, and we got like this, we got say R2 is equal to that also, R2 was there, is still there, but we got like that. So, we have become 0, and then finally, in this we have to see R2's coefficient will become naturally very small. So, by minimum ratio 1, this will go, that you know that this is R. So, this will become as a entering A, and this R2 will become leaving. so you will get some A, okay, that type of thing. So finally you will be getting that basically this one, but still that you are seeing that A's coefficient is 1 by 2, C's coefficient is 1 by 2, A is already there. So better to take now this time C as a entering variable this time, and then you do the row operations, and leaving variable should be, and you can decide that about the leaving variable. So C's coefficient is 1 by B D A. So finally you do that operation and you get basically the solution as 0, 4, 14 by 2. Okay. So you get that B's value is this D. So therefore you remove R1 and R2 here from the picture, and you just do go to that phase 2. In the phase 2 you just write that Z row minus 15 minus 20 0 0 0, but it is again not consistent. So you have to bring out consistency. So for bringing out the consistency you have to see that what 15A plus 20B. So that means A and B both are there. So multiply 50 A by 15, A row by 15, and this is by 20, and then you have to add them. And after doing that type of thing, 15A and then this is 20B. So you have to basically add that, and then you will get a solution. So you will be getting basically this one. So finally we will be getting this type of solution. Solution is 110, and finally we will have to minus 5 minus 10, and this is this thing. Okay. So you have to say that this is 0 0, this is minus 5 0 minus 10, and this one, but you have to maximize it. Okay. So maximization problem, that means E is the most negative. So E can still enter here, and then one can leave. So E has become entering 1, and now you are leaving one variable. So E becomes entering 1, and in a D was by minimum ratio test, D thing has come because 14 by 7 is this one. So you got one table. Similarly you can make the another table, because here also here 0 0 0. So basically you have got this is 0 and this one. So now this is possible, and now what happens that you have to see optimize that most negative. Now even then if it has become leaving 1 and then what happens that here you still have coefficient of that D, that which is most negative. So therefore you do this operation and finally you get the solution. So based on the optimality condition, one of the coefficient in the Z row is negative. Since C has a negative coefficient, it suggests that entering C into the basis could improve the solution. Okay. However, the issue is that no variable can give the meaning the solution is unbounded. So what is the problem here at this stage, that now C's coefficient is negative, but then everything is here basically the positive. Okay, sorry, negative, all the coefficient. So by ratio test nothing can go. So therefore you conclude that this problem is unbounded, and therefore this cannot obtain the solution. So that is what that I want to tell you today. Thank you very much for your kind attention.